So line of best fit's okay, but it's very subjective, of course. What I think is the line of best fit is going to be different to what you think the line of best fit is. So we want to come up with a way where we're going to agree on something. So we've got this thing called the correlation, or Pearson's correlation coefficient. It can be symbolised R if we're talking about a sample, or rho, that's the Greek letter rho, if we're talking about population. Now, when you think about it, because this is pretty much coming from experimental data, it's going to be a sample. Because when you do an experiment, you don't usually test every single possible piece of evidence that we've got. So it's very rarely a population we're talking about, it's usually a sample. So you'll see R used most commonly for the correlation coefficient for that reason. Here's the formula. So the correlation between these two random variables, x and y. On the top there, you'll see this thing called cov. Now, we know about variance. Remember, variance is the expected value of x minus the average squared. Covariance is when we've got two variables. So instead of squaring, we say, oh, what's the difference from the mean of one random variable and the difference in the mean of the other random variable, and multiply it together. So the units are still the same for variance and covariance, but that's what covariance is. And then on the bottom, because I'm talking about a sample, I'm using S for standard deviation rather than sigma. That turns out to be, when you play around with it, you end up with this. So the average of x times y minus the average of x times the average of y over those deviations. As we said, correlation is always in between -1 and 1. So that result should always be between -1 and 1. So if it happens that R is 1, then it's a perfect correlation. Very rare. And if it did happen, you'd start asking some questions, unless it was something really obvious, I suppose. Strong correlation we're defining between 0.6 and 1. A moderate correlation then, 0.4 and 0.6. 0.1 and 0.4, pretty weak. And of course, if it's 0 to 0.1, we say, well, there's virtually no correlation whatever. And if it does happen to be 0, then there certainly is no correlation between the data. You'll notice I put absolute value there because we can have positive correlation and negative correlation. So positive correlation just means they both increase or they both decrease, whereas negative correlation means as one goes up, the other goes down. All right, this is the example we're going to use. Birth weight and the weight at age 21. I've only used 8 people, so I've done a very small sample here. And I guess if we wanted to make some sort of guess about what's going to happen, is there a relationship? Would you think that, you know, big babies end up being big adults and small babies end up being small adults and things like that? So that's what we're interested in looking at here. So the first thing, we're going to construct our scatter plot and then just have a look at that and come to some sort of conclusion. So there it is. I've placed all of that on a scatter plot. Well, it kind of looks linear, doesn't it? So I guess it is suggesting there's some sort of relationship between the two. So, and by my eye, that kind of looks strong. Yeah, it's pretty good. Let's actually work out the correlation coefficients. Right, pay careful attention. We're going to need a few bits of data to create this. So I'm going to let X be the birth weight and Y be the weight at 21. So there's the two pieces of data, X and Y. The other information we're going to need, well, the sum is going to come in handy for working out our stats. So I've found the sum of those two rows. X times Y was in there, so let's multiply each of those ones together. Then x squared is going to come in handy to find the variance on x, and y squared is going to come in handy for the variance on y. So we can now work out our average. Again, I'm not listing probabilities, I'm listing, well, for want of a better word, the frequency. It's not really the frequency in this, but because of that, we divide by the number of scores, like we saw the other day. So the sum was 22.7 for x, divided by 8 people, we get 2.83. For y, it's 54.8. For x times y, that average turns out to be 157. Okay, let's now work out our variance on those. So x squared, but we were actually interested in the deviation, not the variance, so I'll find the square root of that. And for y, And we can now sub it into our formula, and there is 0.78, which did lie in our range for a strong correlation, didn't it? So our eye didn't let us down. Let's have a look at what we call the least squares regression line. The process of coming up with an accurate straight line is known as linear regression. It assumes straight away that the data is linearly related, and that's all we're interested in at the moment. It really works good when there's no clear outliers. So someone before said, should we count them or discount them? For something like this, you'd probably discount them. And what it's doing is it tries to come up with something which finds the minimum of the sum of the squares of the vertical distance from the line to each point. Okay, so that's now the mathematician coming out of me. This is where it comes from. Okay, and the other thing it guarantees is that the line will always go through that point there. Whatever the average of x is and whatever the average of y is, that particular point will be on the graph. So what does it have? Obviously it has a slope. There's your formula for slope. It's the covariant of xy on the variance of xy, but subbing in, playing with that one, I can get it to be the average of xy minus the average of x times y over the variance of x, but I can take that a step further and it ends up being the correlation coefficient. So no, the slope of the line is not just the correlation coefficient. It's actually the correlation coefficient times the standard deviation of the y value over the standard deviation of the x value. That's the slope of the line. The y-intercepts will end up being that. And really, when you look at it, that's no more than y equals mx plus b. So remember I said it must go through the point xy. Ew. So that's just the rearrangement of that. All right, so let's go back to our scatter plot here. So first of all, let's draw in a line of best fit for it and try and work out what that equation is. So let's guess. And I've guessed mine to be about there. Now, I need 2 points if I'm going to find the equation of that. So reading off my line of best fit, I can see that it goes through the point 250. And the other one I'm going to use is the x-intercept, which is 0.27540. So we can find the slope, point slope formula, and there's what I'm proposing the equation of the line is. Let's now actually find the line, the regression line, and see how close I got. So slope, subbing in all those values that we found before, is 5.36. What was my guesstimate?
5.79.
Okay, that's close. The y-intercept ends up being 39.6. So there's the actual equation of the regression line. So if I plot that in, I need a point that it goes through. There's another point. Voila. So wasn't too bad. Let me now show you what they ended up doing in the HSC last year. So it was in this general one as well. It was a common question between standard and 2-unit. Yeah. It was quite controversial too. You might remember it from the end of last year. It was a 5-marker. Right? So the difference with this question to what past HSCs have had, we now have more 5 markers, 4 markers, where they don't break it up into points 1, 2, 3. It's pretty much, okay, 5 marks, there's a lot of information in there. It's for you to dig the information out, use it and come up with an answer. So it starts off, just in case you didn't know, a cricket is an insect. Okay. Yeah. Now, the male cricket produces a chirping sound. Scientists, now they do strange things, scientists, they wanted to explore the relationship between the temperature and the number of cricket chirps heard in a 15-second time interval. As you would want to know this sort of thing. I don't know, scientists. For once a day for 20 days, they collect their data. So based on the 20 data points they came up with, and so here's the information they were given in the exam. They were given a box plot of the data. They were told that the mean temperature is 0.525. And I guess the reason they do that is a lot of people make the mistake of thinking that middle horizontal line in the bar is actually the average. No, it's the median. It's not the average. So the mean was 0.525. And in fact, there was a total of 684 chirps. So there's the information. And see, here's what I'm getting at. They actually gave them the equation of the regression line. They didn't ask them to work it out. So actually, okay, here's the equation of the line. So using that, and they also reminded them that actually that has to go through the average. Now, calculate then the number of chirps you would expect in a 15-second time interval if the temperature is 19 degrees. So that's what they had to do. So they had all that information, put it together, come up with a number. All right. Well, the average, we were told the average was 0.525. Hang on, what did it actually say? It was, let me go back to that information. 0.525 below the median. So 22 minus 0.525, there it is. You'd imagine that was probably one of the marks. The average for Y, remember they told us there were 684 chirps altogether. Divide that by 20, you get 34.2. Now, so we know the regression line passes through that point then. Okay, if we sub it in, we can work out B. So B is this lovely expression. Did I actually bother working it out? Did I leave it as the exact value? I just left it as the exact value there. Well, it's not even the exact value really, because I suppose the other ones are rounded off as well. Anyway, so much rounding off happening in there. But I want to know when x equals 19, so now I sub it into our regression line and I get 29.03, etc., etc. So I'm expecting 29 chirps. 15E's what I'm going to get you to do, because I'm a mathematician, not a statistician, I'd love you to try using the formula and come up with the formula.